For an experiment with a sample space that has a finite number of elements, we assign a weight to every point in the sample space so that the sum of all the weights is 1. And this is what we will do, or is done, to give way to, the idea of probability and what probability of an event is. So let's take a look at definition 2.9 for us here associated with our text. The probability of an event A, probability of an event, I'll say capital A, is the sum of all the weights. Is the sum of all the weights of all the sample points in A. Of all the sample points in A. This is one of the reasons why it's so important to be able to talk about stuff that we've looked at in the past, i.e. listing out elements of a sample space, or particularly counting elements in a sample space. Therefore, let's see here. Now, the probability of an event A, we usually would denote capital P of A, like this. And this has bounds, right? Because A is contained in the sample space, and the weight of all the points in the sample space sum to 1, according to the first paragraph. So this has to be less than or equal to 1. It's quite possible that A has no sample points, but then we would just have 0 associated with that. So it's got bounded between 0 and 1. That case where the probability is 0 would be associated with A being equivalent to the empty set. That would give you a probability of 0. And the other extreme, if the probability of A is equal to 1, well then that means A is just all of the sample space. That would mean A is just all of the sample space. Okay? In simple cases, events that are equally likely, not events, sample points, if all the sample points are equally likely, then the weights are split evenly. Often, all of the sample points are equally likely. And so in order for everything to add up to 1, they're just split evenly. The weights are split evenly. Okay? So, for example, consider rolling a fair die. Rolling a standard, fair, 6-sided die. Right? Then your sample space, you either get a 1, a 2, a 3, a 4, a 5, or 6. And if this is just a standard die, all of these are equally likely, and so the weight associated with each of these would be the same, right? Out of principle. Well, there's 6 outcomes, so what is the weight for an individual sample point? The probability of getting a 1, right, would be 1/6. The probability of getting a 2 would be 1/6. The probability, so on and so forth, of rolling a 6 would just be 1/6. Split evenly, because there's 6 total outcomes, and so we'd have to divide that evenly across the board there. Okay? Now, in this case, where the sample points are equally likely and the weights are split evenly, then you can talk about probabilities of some more complicated events by just simply summing up the weights, and that is something we will formalize here in Rule 2.3. If an experiment can result in any one of capital N different equally likely outcomes. An experiment can result in any one of capital N different equally likely outcomes, and exactly little n of these outcomes correspond to event A. Little n correspond to event A. Then the probability of event A is just little n over capital N. That is, count the number of sample points that are in A and divide that by the total number of sample points in the sample space. So, example continued from above. What is the probability of, well, let's say this. Let's say A, continuing on rolling a six-sided die, let's say A is the event where we roll an odd number on a standard six-sided die. Then the probability of A, well, that's just the probability of rolling a 1, a 3, or a 5. There are 3 of them. There's 6 total elements, so that's just 3/6, or 1/2. Right? So we just get to count which ones we need. That's not what I wanted to do. I wanted to highlight those, right? What elements are associated with A? 1, a 3, and a 5. Here we go. So 1/2 would be our probability. So really, based on this rule here, rule 2.3, based on this rule, when it comes to calculating or computing probabilities, this really ends up just being an exercise in counting. Can you count the number of elements in your sample space, capital N, and can you count the number of elements that are in your event A? And then it's just that simple ratio. So where these questions get harder is where the counting gets harder. And the standard sort of basic, I don't know what the word I'm looking for here, just a real classic example are calculating probabilities using playing cards. So let's go ahead and talk about a standard deck of 52 playing cards. Now, many of you might be familiar with this and even have a deck of cards, nearby. Some of us maybe have never actually held a deck of cards in our hands before. So we're going to do it just once this semester, but I'm going to go ahead and define and write out what is in a standard deck of 52 playing cards. A standard deck of 52 playing cards consists, well, there's 52 cards, and each of those cards is assigned one of 4 suits. One of 4 suits. They are either labeled hearts, diamonds, and both of these are color-coded red if you look at a deck of playing cards, clubs, or spades. Clubs or spades. Okay, so we have 2 red suits and 2 black suits. Hearts and diamonds, clubs and spades. Each of which are labeled with a rank or a number. With a rank or a number. 2, 3, 4, yada, yada, yada. Starts at 2, goes up to 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. And then there's no 11, but we go to what's called a jack, a queen, a king, and an ace. All right. So you have 2 through ace, each in a heart, each in diamond, each in clubs, in spades, for a total of 52 cards, right? Because if you go 2 through ace, you count that up. There is 13 of those. There's 4 suits. 13 times 4 is 52. 52. 52. Okay. And the jack, queen, and king are referred to as face cards. Referred to as face cards. And sometimes the ace, but not always by convention there. And so typically it's just the jack, queen, and king, and the ace is just referred to usually as the ace. If we ever are wanting to include the ace, I'll be sure to try to specify that, but I probably won't refer to things as face cards very often. All right? So, with a standard deck of face cards, let's answer a handful of basic probability questions, okay? A. Let's say you're dealt a hand that contains 5 cards. A hand containing 5 cards is dealt. Let E, capital E, be the event the hand contains 5 aces. Let's find the probability of E. Hand containing 5 cards is dealt from a standard deck of 52 playing cards. Let E be the event that you get 5 aces. Well, as far as aces go, there are only 4 suits. Hearts, diamonds, clubs, and spades. There's only 4 aces. There are only 4 aces. You cannot get a hand dealt with 5 aces from a standard deck of 52 cards, right? So there are no elements that correspond to E. Of all the 5 card hands you can get, the hand that says ace, 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 ace is not possible. Therefore, the probability of E then is 0. Let's say A is the event of drawing a single ace from a standard deck. Let's find the probability of A. Let's find the probability of A. Take a look at this as a slightly different scenario. You are just drawing a single card, drawing a single ace from a standard deck. You are not getting dealt 5 cards now. This is just drawing 1 at random. And so let's see here. Well, how many cards are in the sample space here? What's our total possibilities? Well, you could get any one of 52 different cards. Now, how many of those 52 would correspond to the event A of getting an ace? There are 4 aces, and so that would be 4 over 52, because there are 4 aces out of 52 possible cards, or 1/13. One more, and let's spice it up a little bit here. Okay. Suppose you are dealt a 5-card hand again. Suppose you are dealt 5 cards again. Let's find the probability of getting 2 aces and 3 jacks. Let's find the probability of getting 2 aces and 3 jacks. All right. So, in this scenario, we are getting dealt a 5-card hand. We are not drawing 1 at a time. We're getting dealt a 5-card hand. So, our denominator is going to change, right? We are looking then at a sample space of all possible 5-card hands. So the question that I'll first ask, what is our denominator? What's the total number of possible 5-card hands? Total number of possible 5-card hands is, we'll call this capital N. Well, let's think about this. You need 5 cards. They're coming from a pile of 52. And I'll ask you this. Does the order matter when you're getting these cards? Well, the answer is no, because I'm getting 2 aces and 3 jacks. It still satisfies my event if I have 3 aces and 2 jacks, right? The ordering does not matter, so this is a combination. 52 choose 5. 52 choose 5. And we can run that number through a calculator here. This ends up being 2,598,960. All right, that's the total number of possible 5-card hands. So then what is the number of 5-card hands that satisfy our event? How many ways can we get 2 aces and 3 jacks? 2 aces and 3 jacks. Well, let's think of this as a step-by-step process. First, you got to get 2 aces, right? So, number of ways of getting 2 aces. Number of ways of getting 2 aces. From 4. Because think about this. If you were going to do a tree diagram for this, right? If you're going to do a tree diagram of getting 2 aces, you could run through the possibilities of getting the ace of spades and the ace of diamonds, or the ace of spades and the ace of hearts, or the ace of clubs and the ace of spades, or the ace of hearts and the ace of clubs. And you could run through that, right? You are getting 2 aces. There are 4 of them. 2 aces from 4. 2 aces. There are 4 of them. You need 2 of them. Again, the ordering doesn't matter here. This is another combination. 4 choose 2. There are 6 ways to get a pair to pair up the aces. Now, for each of those 6 ways of pairing up the aces, what are the combinations of getting 3 jacks, right? Number of ways of getting 3 jacks from, again, there are 4 jacks to pick from. That would be 4 choose 3, which ends up being 4. Okay? So we're going to use the multiplication rule here, right? Because for each of the 6 ways we can get 2 aces, there are 4 ways that we can also tag on 3 jacks with that. So via the multiplication rule for counting sample points, there are little n 6 times 4, or 24 ways of getting 2 aces and 3 jacks. 24 ways of getting 2 aces and 3 jacks. So, the probability then of getting the 2 aces and 3 jacks is 24 over 2,598,960. Which, if you want to round that off to a decimal to get a percentage, be 0.0. What do we got? 1, 2, 3 zeros, 4, 5 zeros. 0.5 zeros and a 9. Very, very, very small percent. Well under a 1% chance of getting 2 aces and 3 jacks. Those of you who are poker players will be familiar with 2 aces and 3 jacks as something that's called a full house type of hand. That's not all full houses, but it's just that specific full house, which is a very high ranking full house, mind you. Okay? All right. We're going to leave it there. If you do have any comments, questions, or concerns about the content covered in this video, please post that in the discussion thread below. Otherwise, we will see you in the next video.